Okay, good morning. In this video, I'm going to consider exercise 112, which is to be found on page 38. In this exercise, we are dealing with the following function. Here, you see the function equation. F of x is defined as 48 divided by x squared plus 12. The exercise consists of two parts. The first part is about curve sketching, so we need to find the zeros, the stationary points, and the points of inflection. And the second part is going to be an optimization problem. So let's start with part A. So we're supposed to find the zeros, the stationary points, and the points of inflection. So let's start with the zeros. So the function here is defined by a fraction, and as said several times, a fraction is 0 just in case the upper part is 0. So 48 can't be 0, which means there are no zeros at all. Let us continue with the stationary points. So the stationary points are the solution of the equation f prime of x equals 0. So we need the first derivative. Let's see. Well, the function here is defined by a fraction, so we are going to apply the quotient rule to get the derivative of this fraction. So here it is. First, we take the derivative of the upper part. The upper part is 48, which is a constant, so this is 0, times the lower part, minus the upper part, times the derivative of the lower part, which is 2 times x. The whole thing divided by the lower part squared. So we can simplify here a bit. I mean, this thing here is 0 times something which is 0. Then we can here multiply, which leads to minus 96x divided by x squared plus 12, and the whole thing squared. So this is the first derivative. Now, let us set that first derivative equal to 0, leading to, well, this thing here is 0, which means the upper part is 0, so minus 96 times x equals 0, which leads to x equals 0. So we have a stationary point at x equals 0. Now we need to know what we have here, whether we have an extrema or a saddle point or whatever, which means we need to take the second derivative of f. F double prime of x equals, well, here we have f prime. So once again, it is a quotient, so we need to apply the quotient rule once again, taking the derivative of the upper part, which is minus 96, times the lower part, minus the upper part, times the derivative of the lower part. And to get the derivative of the lower part here, well, we need to apply the chain rule. So it's 2 times bracket x squared plus 12 times the derivative of what is inside the bracket, which is 2 times x. And the whole thing divided by the lower part squared once again. So it's x squared plus 12 to the power of 4. Now if you consider this fraction here, well, we have here, here, and here always the same expression, so we can reduce 1, and here we have to the power of 3 left. So this leads to minus 96 times x squared plus 12 minus 96 times 2 times x divided by x squared plus 12 to the power of 3. Okay. So what are we going to do next? Well, simplify here, leading to minus 96x squared minus 1152 plus 384x squared divided by x squared plus 12 to the power of 3. Now we combine these two expressions, leading to 288x squared minus 1152 divided by x squared plus 12 to the power of 3. So this is the second derivative here. So now let's see. We have found our stationary point here at x equals 0. So we plug that one into the second derivative. Well, then we get minus 1152 divided by 12 to the power of 3. This is, of course, negative. So we have a Hochpunkt with x-coordinate 0 and the y-coordinate, well, just plug 0 into the very function equation from the beginning, leading to 48 divided by 12, which is just 4. So we have found a Hochpunkt with coordinates 0, 4. The last thing to do is to find the points of inflection. Well, in order to get these points, we set the second derivative equal to 0. So the second derivative was up here, still defined by a fraction, so we can just set the upper part equal to 0. Like this. And then we take the calculator, for example, and solve for x, leading to x equals plus minus 2. So we have 2 points of inflection at plus and minus 2, and the y-coordinate is in both cases just 3. So this was the first part, curve sketching. Now we are going to continue with the second part, which is about optimization. So here is part B. In a first step, we draw the graph of that function. Okay, so this is the graph. And well, it's not that clear from my picture, but if you consider the graph on the calculator, you see immediately this graph here is symmetrical with respect to the y-axis. Okay, so what do we want? Well, we inscribe a rectangle here below the graph with 2 vertices on the x-axis and 2 vertices on the graph. So we add a rectangle like this. And what do we want? Well, we want the area of that rectangle to be maximal. Should be maximal. So this is our problem. Now, how can we calculate that area? Well, the area of that rectangle is just given by the length of the length of AB times the length of BC. And now, since this graph here is symmetrical with respect to the y-axis, this line here is precisely half of the whole line. So instead of this formula, we can also take the length of this line from the origin to B times 2 times the length of BC. Okay. So now, what do we do next? Well, of course, we introduce coordinates. Let's start with B. B has coordinates x0. We don't know anything about the x-coordinate of B at the moment, so that's just it. What about C? Well, C is coordinate x, same x-coordinate as B, and the y-coordinate is y. Then what about point D? Well, point D has the same y-coordinate as C, and well, since this here is precisely half of the whole line, the x-coordinate of D is minus x. And of course A has therefore also coordinates minus x, 0. So let's see. This means the area of the rectangle is now, if we use this formula here, is given by x times 2 times y, or to put it otherwise, 2 times x times y. So the only thing left to do is to find the relation between x and y. And of course this relation just results from the fact that point C lies on the graph. So this means y is given by f of x, or 48 divided by x squared plus 12. So now we take this thing here and plug it into this equation here, and then we get the following formula for the area. The area equals 2 times x times 48 divided by x squared plus 12. Simplifying a bit leads to this. And this here is precisely what we need. We have a formula containing one single unknown that describes the area. So we take that formula and take this first derivative of that. Once again, we need to apply the quotient rule. Minus the upper part times the derivative of the lower part divided by, and this should be 0. And now here's something important. Since this whole thing here should be 0, well, there's no need to simplify here the lower part, because that anyway drops away if we set the whole thing equal to 0. So if the whole thing equals 0, the upper part has to be 0, so we can just ignore the lower part. So this is this, and now we eliminate, let's say we take this thing here on the other side. Now we divide by 96. Leading to this. Now, this means 12 equals x squared, so this means that 12 equals plus minus the square root, this means that this plus minus the square root of 12 equals x. So, and with this we're done. We have assumed from the very beginning, since x is the x coordinate of b here, that x has to be positive. So x equals the square root of 12. So let's see, what was our task? Well, our task was to find the coordinates of C and D. So we get C has coordinates square root of 12, 0, square root of 12. Plugging the square root of 12 into the function equation here leads to the y coordinate of 2. And D has coordinates minus square root of 12 and also 2 as a y coordinate. That's it.